Thank you for the invitation to present at the symposium and also exhibit in the Biennale. What I want to talk about today is to try and give some context to the project, the prototype that's in the exhibition. It's a composite fiber prototype. The lineage of this goes through a series of projects which I describe as the Agentbody prototypes. I'm going to track through some of those and try and explain why it is that we're exhibiting the project we are now. To give a wider context, there's two halves to my practice. One is Kokuja, which is a research lab. It's a collaboration with Robert Stewart Smith. And the other side is my architecture practice, Studio Roland Snooks. Now, the research lab deals with algorithmic design and robotic fabrication. And this tries to be a sort of an engine for innovation, whereas the practice is trying to take those innovations and apply them to real building projects. So we work in terms of private commissions, both at the domestic and commercial scale. We also do a lot of design competitions, and we collaborate with other architects to work on larger construction projects. The thing that's probably most interesting to me, though, about the work that we're doing is the highly intricate, complex, and sometimes strange geometries that we're working on, and their expressive capacities. Now, this work is coming about through an algorithmic approach that I describe as behavioral formation. Now, behavioral formation draws on the logic of swarm intelligence and operates through multi-agent algorithms. Swarm intelligence describes collective behavior in flocks of birds, schools of fish, social insects, systems in which individual entities, I describe them as agents, interact to give rise to the emergence of a self-organization of behavior which emerges from these interactions, and it's somehow greater than the sum of its parts. So in this type of example, the agents, the birds, they have no understanding of the overall flock. They have no intention at the large scale. What they're attempting to do, though, is simply interact with each other based on a few very simple behaviors. These behaviors can be described algorithmically, things like separation, cohesion, alignment. Now, in taking this forward into architecture, I'm not interested in trying to make architecture somehow biological. I'm not interested in trying to make architecture swarm or flock-like. My interest is how can you use a distributed system of emergence or a bottom-up system of design. So my interest is how can we take the intention of the designer, program it into a series of behaviors, and look at the way those behaviors interact to give rise to the self-organization of design intention. So this is an alternative to trying to think about designing the building or the object at the large scale. We don't sit down and model or draw things directly. What we end up doing is we look at how do we write the underlying rules for them. Now, having said that, there's also a more complex interplay of direct decisions and bottom-up decisions. Swarm algorithms are based on a point, a single agent. Now, making buildings from clouds of points is a very difficult thing, so we've started to look at the way agency can be encoded into different substrates, so into lines, into meshes, into something we call bodies. And it's this agent-body algorithm that I'm going to talk about today mostly, and it's what most of the projects come from. Now, the body is basically something where the thing is an agent in itself, but then it has limbs, it has these tentacles or arms and legs. You can think of this as something like the way ants will make ant bridges. The way the ants connect their arms and legs together, and they become a piece of structural or architectural geometry. So this is an algorithm that underlies a lot of the work that I'm going to show today, and it's an algorithm in which the design intention is about the emergence of a coherent, what I describe as a manifold surface from a cloud of points or a cloud of bodies. This is something that we've been, the multi-agent work we've been doing, or the behavioral formation strategies, is something we've developed, I guess, almost 15 years ago. And throughout that work, it's generated these types of geometries. But it's been over the last 3 or 4 years where our interest has been in building these things. And we began to ask the question, if we can't build these things, should we simply stop designing them? And so our strategy or our attempt has been sort of twofold. One has been through robotics, and I've established the Architectural Robotics Lab at RMIT University, and the other approach is through fiber composites. Behavioral formation is based on this idea that very small things interact to give rise to emergence at a larger scale. So what could that very small thing be? Could it be as small as the fiber within a composite fiber surface? So we started looking at the way fibers might behave, the way they might interact. We looked at different types of resins and fibers. This is an early prototype we did at Tonji University with students in a workshop from 2011. And then since then, we started to look at some of the architectural implications of this. What type of architecture might this make? What can you suddenly afford to do that you couldn't simply do reasonably or feasibly previously in terms of structure? We're looking at the way these thin veins start to create a certain characteristic of surface, certain affects, certain moods and atmospheres. We're interested in their translucency. And of course, how to build them. When we first started building these, we're building them in what is quite a traditional boat building technique. So we're milling molds, and then we're laminating surfaces onto them. Since then, our work is becoming increasingly complex, and there's a series of other strategies we're engaging. This project, done at the same time as the previous one, looks at a strategy which is quite important to our work, which I describe as something that's polyscalar. So in other words, something that happens at numerous scales. And it's this idea that as you zoom into something, you start to see the same behavior or the same patterns, the same geometries at different scales. In making a prototype for this project, our interest was less in how composites might be performative in the way that Maritza was describing. We're not so interested in the relative weight of something or its structure, although of course these are important characteristics in terms of how we might achieve the types of buildings we've been designing, but it's more about the expressive qualities. And we're interested in the sort of the expressiveness or the dirtiness, a whole series of characteristics which exceed the digital. We're also interested in the scale at which you get down to, this idea that you might get down to a very fine ornamental scale with these fibers. And that was a project that was done in Helsinki at a workshop a couple of years ago. And projects from RMIT University, where we're looking at what is the small-scale characteristic of some of these veins. Now, up to this point, all of the prototypes I've shown you look at the strand or as a underlying geometry. The projects that I want to focus on, though, today are actually using the agent bodies. This was one of the first studies, and these next two projects I want to concentrate on and pause and spend a bit more time looking at. So this project called the Composite Swarm, this is trying to compress form, structure, and ornament down into one irreducible whole. So if modernism was often interested in the way form, structure, articulation could be separated out into discrete systems, I'm interested in the way complex systems are capable of negotiating many different things at once in a single piece of geometry. So this is an idea that instead of treating, say, structure as a piece of geometry, or articulation or ornament as geometry, these are behaviors. And these are behaviors which interact, and to give rise to something which is synthetic, something which is irreducible, but has those qualities or characteristics or performance criteria embedded within them. So again, this is using a similar algorithm. It's a cloud of agent bodies. These bodies are swarming around and trying to make a manifold surface, a coherent surface. And in doing so, they're connecting their limbs, their arms and legs, together to make continuous lines of structure. And it's this that gives the project its inherent strength. You can see that those bodies then get laminated within composite fiber. This gives you some sense of the detail of that. And there are 3 different types of bodies that were used in this project, and those bodies were cast out of polyurethane foam. Now, an agent body is, in the way that we describe it, is a series of strands which have agency built in at numerous points to it, and so they can kind of respond to the things that are around them. And I want to talk a little bit about the way we fabricated this and the way that led to subsequent projects. So this involved 3-axis and robotically milled foam, which was then pieced together and coated in epoxy resin. These are the cast polyurethane agent bodies, which are then applied between layers of fiberglass fabric. That's then covered with a vacuum bag, resin's infused through it under vacuum, and this is at the point where it's about to be demolded. Now, of course, something that Maritz was alluding to is the problem with the mold. There are a lot of efforts placed in this mold, which is then destroyed afterwards. It's one of the saddest points of the project as well. You've labored over making this thing, which then gets sort of hacked to bits with hammers and saws. But hopefully it leaves something which has a whole set of qualities behind. And so we're interested in the translucency of these materials. This is a good slide in which to describe the way the structure works. The fiberglass is very thin. This fiberglass is less than a millimeter. It's about 0.85 of a mil. And it's incredibly flexible, incredibly floppy. Then the polyurethane bodies are made from flexible foam. They're also floppy. And this idea that you can take two very weak, very flexible things and put them together to make something that's very rigid. And the way that works is that the polyurethane body imparts a small corrugation in the geometry. So it's this idea that strength doesn't come from material. We're not using a more advanced material to make it stronger. We're simply changing the geometry to make it stronger. And the idea, and you can sort of see that these corrugations, the way they run through the project, you can link that back to the way the behavior of the bodies work. The arms and legs of those agents are connecting together so they can make continuous lines of structure. Now, of course, in doing so, those lines of structure, those bodies, are excessive. They're not purely about structural optimization. They are working structurally, but there's a certain excess to them, and this is something that we're interested in terms of its expressive qualities. That's quite a small project. It's about 2.5 meters tall, and as I said, less than a millimeter thick. The same client came back to us a year or so later and said, could we make a larger installation? And this one we designed for them is almost 70 meters. So the previous one was 7 square meters. Now, as soon as you go up a scale of 10, you can no longer rely on what was basically a handcrafted project. Yes, there was robotic milling involved, but there's a lot of hand labor. So we had to work out some way of making things more efficient. So we call this project the composite wing. It's made up of a series of 3 pieces, so 3 large wings that become tables. This is the last render we made before we started to get into the nuts and bolts of how you actually resolve and build this project. So from this point onwards, there's a lot of rationalization that went on. This is a bit hard to see, but one of the biggest problems we had, of course, with the previous project is making the mold. And so we realized we couldn't make 70 meters worth of mold. In boat building, a mold costs 15 times the price of the thing that's made from the mold. So within architecture, that's generally a fairly difficult thing to do. So what we did is we made 8 parts, and these 8 parts come from a single mold. Well, in fact, 5 of them come from one mold, and the other 3 are just made on a flat sheet. So, however, you'll notice that the design has no real repetition in it. So what we're interested in doing is how can we use a repetitive process like a mold, but get something that seemingly doesn't have repetition? And the way we did this is by cutting different edge profiles and then looking at the way these interact in order to give something which is seemingly non-repeating. The mold also had to be made out of something more robust than foam, as that we're making 5 parts of them. So it was milled out of timber. It was profile cut from MDF. Those were then robotically milled and CNC milled to get them to be smooth. Those parts I was showing you are at the bottom right-hand corner of the image. Then there's a whole lot of the other parts of the mold which aren't doubly curved, which are flat and can be built by carpenters. This is the final mold. It's like a small house, really. It's about 5.5 meters by 6 meters by 2.8 meters. It's quite a big structure. So even though there's some repetition in terms of the curvature of the surface, there's no repetition in the agent bodies. And one of the reasons for that, and they're at 2 scales. The larger scale you can see here is milled from foam, and the smaller scale is robotically extruded with silicon. Now, one of the reasons why we couldn't do repetition, apart from our sort of disinterest in repetition, is to do with the structural behavior of these things. This is a structural analysis which is looking at bending moments on the surface, the underlying surface. And then you can see here, this is a diagram describing how the agent bodies are orientating, they're sort of swarming across the surface, they're orientating themselves in the direction of the bending moments and reaching out their limbs in that direction and also scaling based on the amount of deflection. So this is a way in which the form of those agent bodies are not, again, purely about structural efficiency. I'm interested in a whole lot of other expressive possibilities of these algorithms, but what they're doing is they're always responding in a structural way. Again, these are milled, robotically and CNC milled. Some of these are milled both front and back, others are milled just out of flat sheets. Perhaps the more successful, and that was quite a labor-intensive part of the process. There's a lot of milling. A more successful part of the project was probably the direct deposition or the extrusion. So this is where the smaller scale agent bodies are extruded robotically with silicon. Our original intention was to extrude these directly onto the mold, and then of course we realized that because the silicon is flexible, it's much easier to extrude it onto a mesh, which could then be placed onto the mold. This is our fairly crude extrusion tool. And there's the mold. So this is how the process works. Somebody would mark out the placement of these things. Then it would be laminated. The large and small bodies would be placed into the mold. And then additional layers of fiberglass would then be added to it. These pieces would then be trimmed, put on the back of a truck, and installed in the gallery. Our original intention was to show this project at the Tallinn Architecture Biennale, but unfortunately the pieces were just big enough to fit in a shipping container but wouldn't fit through the door or the stair of the gallery. So we're showing a smaller prototype. So the project has two sides to it. One is smooth, is the side that comes off the mold. And then the other side is, the bumpy side is the side which has all the detail. And again, it's a project in which strength comes from its structural depth. So those beams, of course, are made from foam. They have no structural integrity of their own. But by putting all of these corrugations into the surface, it takes on significant strength. So the deflection on the largest wing would have been 5 meters if it was just the fiberglass under its own self-weight. But with all the beams in it, it was about 10 centimeters. Which is perfectly, reasonable thing for an installation. Okay, I want to quickly show a couple of other projects to explain the way we're trying to realize these agent body algorithm geometries through different materials. So this is a prototype that we developed for the field constructs competition that Igor was explaining. This is taking a sort of highly generative version of the algorithm and building it from flat sheet material. That's all laser cut. And this is another one. This is a project we built in January. We call this one the Brass Swarm. And this is looking at the way, instead of trying to build from surface, we're building from line. And this allows us to sort of escape the surface, have greater structural depth. And this is being generated through, or built through, robotic fabrication. So one of the keys to this project for us was how do we take the behavior of the robot and build it into the algorithm? So what this animation is trying to show is a series of different types of analysis we do on the thing that we've generated. So again, it was generated through this very wild, highly generative swarming algorithm, but at the same time, the whole thing is conditioned by all these series of rules. So we're analyzing it constantly for things like maximum bending, minimum, maximum lengths of segments, angles of connectivity. There's a whole lot of things we had to look at to see whether they're actually possible to be produced by the robots. Then we took those behaviors of the robots and we encoded them into the behavior of the generative algorithm. And this is an idea that although it's being generated by something that's quite wild, it's being constantly conditioned by something that's very pragmatic. And I guess this is one way we try and describe our work, and we think it's perhaps different from some of our contemporaries, is that pragmatic concerns never drive our work. Pragmatic concerns simply condition and make these things realizable or possible. Okay, so this is being bent in the Architectural Robotics Laboratory at RMIT. And then those things are then welded. This photographs of some of the details of when, in fact, it's brazing. They're brazed together. Okay. After doing that project at the, that was exhibited at the Shanghai Architecture Biennale, we were asked by Tongji University, also in Shanghai, to then, we're asked if we can scale this project up. And so we produced this, I guess, much faster project, but this is trying to look at what happens if we take this from a sort of sculptural scale up to begin to think about it as an architectural scale. So this is a small pavilion. It's quite a rapid process to develop. All the rods for this project can be bent in 24 hours. The assembly of them currently still takes about 5 days to assemble, and perhaps a team of about 8 people. The next step in this work is going to be how can we get the robots to bend these, but then also begin to assemble them. Fabrication is not really the problem in sort of complex geometry architecture. Actually, assembly is the problem. And so that's the thing where this work really needs to go towards. One of the reasons we're able to scale this up, in the brass swarm, we have rods that are about 900 millimeters long. This is twice the length at 1800 mil, and they're aluminium. We're able to scale up because we went from using very small robots to, I guess, medium-sized robots. These were 2 robots we were using at Tongji University. Gives you some sense of the details. This was because it was a very temporary project. It wasn't welded together. It was mechanically fastened. This has led to another project we've been working on recently, which is yet again another scale up. This is a public art project that we're looking at in, again, Shanghai. And now this is obviously not a prototype. The reason I show this image, this is a project we did in January. It's a competition entry that we lost for a bridge over the River Thames in London. And what we're trying to do is we're trying to imagine a bridge which is not one of the typical models. If the typical models of bridges are either arches, suspension bridges, or trusses, these are all models which directly try and resist load. We're trying to ask a different question and say, what if we had a cloud of things? What if we had a cloud of things and each one could understand, is it working at tension or compression? What type of tension and compression it's working on? What are the loads and stresses on it? How would it then adapt its body to be able to deal with this? We worked with Bollinger Grumman on the engineering of this, and they came back to us and said, actually, this should be about half the weight of a traditional bridge, because we're using very thin rods. The reason this project was perhaps unbelievable to many is because of the complexity of the geometry. But I guess what we're trying to prove through doing all these prototypes is that when we do a project like this, it's not completely whimsical, it's not farcical, it's not something which may or may not be possible in the future. We're very really trying to develop the processes within our laboratory that can demonstrate that doing these types of projects are very realistic and very feasible. Thank you.